And good morning, everybody. I am delighted to see so much participation in this workshop. And I'd like to thank Rigaku, of course, for this. It's a nice idea also because all major events this year, as you know very well, have been postponed to 2022, including the European Powder Diffraction Conference, which is probably the most relevant event in the field of powder diffraction. So I hope I will be able to entertain you for the rest of this hour or so. And much of the following was in these recent review papers, and much more can be found in the literature I have produced, as Artem said, over the past about 30 years. But please feel free to ask me for articles in the future. I mean, most of which are accessible through ResearchGate. So you can even just download them. Here, however, you have a list of websites you might like to look. So let me start from the beginning, when in the second half of the 1960s, Hugo Rietveld published two articles destined, not immediately, but over time, to deeply mark the development of powder diffraction, modern powder diffraction. Until that time, structural solution and refinement were almost entirely based on single crystal studies. And this was due to the impossibility of separating the contribution of the powder spectra, and if not for very simple, highly symmetrical structure. With powder diffraction, integrated intensity was usually employed, often for groups of overlapping peaks. So there was a lot of loss of information. This made powder diffraction of little interest in this area of diffraction in crystallography. As you can read, Rietveld drew the inspiration for his method from the observation that the line profile of the instrument at the facility for Newton diffraction, where he operated in Petten in the Netherlands, is approximately a Gaussian. And it must be said, however, that in those days, the use of computers and their programming was already known in the scientific field, but if not to everyone, at least, I mean, not only for professionals. Rietveld was able to write software to model the measured neutron pattern, and using Gaussian line profiles and using the width relation from Giuseppe Cagliotti, who was known already at the time for neutrons. In 1917, with available computer, Rietveld was able to refine just a small number of parameters, limiting the description of the line profiles to overlapping peaks. As you see, so squares in the graphic, those are just for sufficiently isolated reflection that were accounted for as integrated intensity. This was a proof of concept, as I said, destined to leave a mark, but not in the early years, in which Rietveld work was essentially ignored, and powder diffraction was very far from the classical approaches of crystallography. So people were not even so much interested, let's say. 2 years later, Rietveld already described how the analytical profile could be corrected to model the asymmetry of lower angle reflections by introducing this parabolic correction term. And as you see, showed an entire pattern refined with this method, demonstrating in numbers, I mean, an advantage in the statistical quality of the result over the use of integrated intensity, which was, let's say, the paradigm at that time, as well as an excellent agreement with single crystal results. This was very important. In addition, since the beginning, Rietveld indicated the possibility, although for him not immediate, to extend the method to X-ray diffraction patterns. In the full form, this, however, was destined to happen only 8 years later, with the work of Malmros and Thomas, as you see here, where they, better than a Gaussian profile for X-ray powder diffraction, proposed a modified Lorentzian, and always correcting for asymmetry, especially for the low angle reflections, which is quite normal for powder diffraction. Here you see some details. And then again, on the same year, actually is the same issue of the same journal. There's a nice coincidence in science sometimes. One of the first works in this subject area of Ray Young, and among the co-authors, you can see Bob von Driel, who is the author or co-author of Jesus, one of the most popular software for the Rietveld method to date. And Young and co-workers already recognized that something better than the Gaussian and the Lorentzian was needed. As you see, a more sophisticated profile representation will no doubt be desired later. But at that time, the concern was just on the collection of integrated intensities. By so as you can see, the profile was not so well modeled at that time. Okay. So as you see, Gaussian profiles fall off too rapidly and Cauchy too slowly. So they were aware that something was not working well. So in 5 more years, by 1982, several line profile functions had been proposed and tested. This is a well-known paper by Young and Wiles. And on all of them, void-type function emerged. Convolution of a Gaussian and the Lorentzian function, and pseudo-void, which is a linear combination of the same, which is very similar to the void curve for practical uses. And then finally, around, let's say, 87, 89, a particular representation of the pseudo-void was established, and with the parameterization of the Gaussian and Lorentzian components of the full width at half maximum, FWHM, one way of representing the peak width. And here you can see expressions for the Gaussian and the Lorentzian and the total full width at maximum. All the details of these so-called modified Thomson-Cox-Hastings or TCHZ pseudo-void are shown in the 1993 book of Ray Young. But essentially, the same function is still quite popular today, as is one of the most recent handbooks on Topaz, which is one of the most used software for Rietveld method that I personally like. You see in the book from Robert Dimmebier and colleagues, which is 1 or 2 years ago, still the TCHZ function is basically the main choice. So the question is, why is it so popular and successful? First of all, this TCHZ works well or acceptably to determine the area of the diffraction peaks. And I remind you that this is always the primary function within the Rietveld method. For years, and probably still today in many cases, the information content of the profile, width and shape, which is mainly the instrument and the microstructure of the sample, was simply not of interest. Second point, the parameterization of the full width at maximum in terms of cos, theta, and tangent theta function was very easy to understand and easily related to size and strain effects, respectively. In fact, it is quite immediate to verify that the 1 over cos theta derives straight away from the Scherrer equation. This is the old way it was written, the Scherrer equation, if you like. This is a more modern form of the Scherrer equation. So the cos, 1 over cos time comes from that, whereas the tangent term comes from the strain. If you just differentiate the Bragg law for constant wavelength, you can obtain the effect of a uniform strain that we know very well is just shifting the peak position. Is a uniform strain. And by similar argument, let's say in a sort of heuristic way, you can consider the case of a variable strain, whether of the second and third time, if it is within the grains or from grain to grain. However, it's known that this broadens the peaks. And as I said, you can extend this tangent law to the peak width, full width at maximum, and now to the microstrain, which is basically the RMS strain, is the standard deviation of the strain distribution. And based on these simple expressions that you can even think of combined, I mean, together, and this is the basis of so-called Williamson-Law method, it is very common in Rietveld refinement software, including Topaz, that they have routines to provide an estimate of the size and microstrain. However, these Voitian or double Voitian line profile often fit the experimental line profile well, but the interpretation of the refined parameters in terms of size and strain is substantially arbitrary, if not erroneous sometimes. The underlying assumptions are too simplistic, and this for quite many reasons. I will not go over all of them, but clearly there is problems because of these terms of size strain have been used in a simple additive way, that the Gaussian profile has problems with the size effect, that microstrain is not a constant, but it's a function of L. We will see this later. And then what about anisotropy, size dispersion, size shape, and other issues? So ultimately, the Voitian line profile, which often includes also correction for profile asymmetry or various types of aberrations, are good insofar as they fit the data. But care, real care, must be taken in giving a physical meaning to the refined peak profile parameters. So, actually, it is interesting to note that as early as in Young work in the 80s, the need for going beyond this simple and somehow arbitrary description of line profile already emerged. So, actually, a more reliable and complete description of the line profile has been known since many years, here from the well-known papers of Leroy Alexander in 1950 and following years, where the various contribution of the instrumental profile and the microstructure of the sample combine to form the observed profile H through a convolution. This idea of composing the line profile in this way has been well explained also in the textbook. You can refer to the Clark and Alexander book for details, especially for the instrumental profile component. And in fact, for the instrumental profile, the idea was taken up by Bob Cherry and Alan Coelho in the 90s. And for the G part of the profile, as you see here in their 1992 paper, each optical component of the instrument forming the G profile can be adjusted, if not fixed, if some parameters of the instrument are known, like, I don't know, the goniometer radius, the height of the beam. So you can refine or keep constant some parameters. You can include sample absorption effect, which actually is included here just for convenience, because strictly speaking is a sample effect. So in the end, the idea of Alexander and Clark has been implemented, taking advantage clearly of the well-known evolution of computers that by the 1992 were already available. Over the years, this approach, which is called Fundamental Parameters Approach, FPA, has been refined, adjusted, and perfected by Alan Coelho within the software Topaz. And in these, for example, and you can find details in these recent books, as I say, for example, you can see the case of how to model the instrumental function of a diffractometer, which is quite common. with a strip detector, no monochromator, and unfiltered copper K-alpha radiation, copper radiation, let's say. Here you can see the details. All the necessary contributions are implemented in the macros for topaz, including fine features like the tube tails of the anode of the X-ray generating tube, the absorption age effect because of the filter and the lack of monochromator, and asymmetry that mainly is due to axial divergence in this case, as well as a description of the emission profile, which can be made not just with the 2K alpha 1 and 2 component, but in this case with 5 components. It is all extremely simple and effective with this FPA approach, fundamental parameter approach. However, you can do things very often in a simpler and, let's say, more agile way. But I'm talking of this possibility because I'm using this in the next slides for simplicity. If the instrument has good optics, it's possible to produce a reasonably symmetrical instrumental profile for which you can use a pseudo-void function with the big width, sigma, you see is half width actually, and eta, which is related to the shape, which can be easily parameterized as shown here. So basically by fitting to the pattern of a standard, which is now the lanthanum hexaboride from NIST, then you can obtain these relations which provide you the instrumental profile at any needed angle. So this is what we call a parameterization. And then also a correction for the peak position, which is this delta to theta, which is directly from books of Art Wilson, and is another way to simply represent the instrument. The same approach is also shown here for the instrumental profile of argon 11BM beamline, modeled by this simplified approach, and gives an almost constant profile shape. You see the flat dotted line here, and the width which is around 100 of a degree, while aberrations basically are absent. There is no aberration at all in the position. Now, returning to the convolution approach, we have seen how it is possible to represent the G profile with a simplified approach or using the fundamental parameter approach. As I said, with some software like Topaz, you can freely choose which one you want to use. For the F component, sample related to the microstructure of the sample, it is convenient at this point to introduce the Fourier theorem for convolution. The convolutional profile components is transformed basically into a product of Fourier transforms, which is computationally much simpler and more effective to deal with. This is basically the idea of the so-called WPPM, whole powder pattern modeling approach, which I have developed over the last 20 years or so, and which is now available in the form of macros for Topaz and in other softwares as well. But let me say for Topaz, it seems to work pretty well. As you can see, in the simplified approach for the G component, the instrumental profile, we can use the analytic Fourier transform of the pseudo-void function, which is by simple expression, and use the parameterization that I have already shown before. This means basically that once a standard has been analyzed, this can be fixed and used for any application. Now, what about the microstructural terms? For the size effect, the Fourier transform is given by the so-called common volume function. You can see details in Wilson's work in the 1940s. Here we see the expression for a spherical domain. Basically, this common volume is, as you see here, the volume shared by the dot crystalline domain, and the same one translated the distance L along the scattering direction. So, since it is a sphere, the shape is completely isotropic, and so this is just a function of L, the Fourier length, and D, which is the diameter of the sphere. So pretty simple example. So if Fourier transforms for necessary for any other shape, you proceed basically in the same way, identifying the common volume function, as you see in this schematic drawing here. And now, of course, the function, the Fourier transform, is also a function of the Miller indices. So it will be different for different diffraction peaks, and some shapes parameters describing the specific geometry. In principle, you can use any shape. The important thing is that for different direction, of course, the expression changes, as I said, and they can be generalized to any shape. So in principle, you can calculate for any shape. The expression can be further generalized to the case of polydisperse systems. That means when you have a presence of different sizes, and for example, if you use a log-normal distribution of the length parameter, for example, of the diameter of the spheres, then you have a mean and a variance, mu and sigma square. And in this case, the Fourier transform for this size component of the line profile is this expression, which might look complicated, but in the end, for a computer, is not such a big deal, and is dependent on L, the Fourier length, the HKL if the shape is not spherical, mu and sigma for the given distribution. You might even use a different distribution if you like. This expression holds true for any other convex solid with a single size parameter, like a cube or a octahedron, tetrahedron, but basically you can extend it to any shape and with some suitable modifications. What about the strain? Expressions are also available for the effect of inhomogeneous strains, which involve the mean square displacement or the mean square strain. The expressions are not simple because actually, contrary to what you have seen for the simplified expression for the full width at half maximum, it is necessary to consider the strain or the displacement, but what we need, as you read here, is the variance. For each distribution for any distance L between pairs of atoms within the crystalline domain. And then you have to do this for each crystallographic direction in the domain. It is not at all so simple. However, we can profit of the work of Krivoglass and Wilkins. This is the model you can use with the parameters you can read to describe, for example, the effect of these locations. Then you introduce the parameters of the slip system, and you can calculate an average contrast factor to consider the anisotropy of the elastic medium and of the type of line defect. In fact, you can then calculate this for different dislocation type. Now, what is in the end that you are handing within your Rietveld refinement? Well, you will end up with refining the average dislocation density, this effective outer cutoff radius, and which type of dislocation, screw, age, any mixed one. However, if the strain source is undefined or there are multiple strain sources, which is very frequently the case, and if it is not dislocations at all, then we can use another less specific phenomenological model that I call PAH, with the P to remind of Nikolai Popa, who unfortunately recently passed away, and Adler and Uska. And by the way, Uska has been probably the last pupil of late Professor Warren. Okay, with this model, it is possible to refine the coefficients of these invariant form that is called gamma, which is identical with the average contrast factor, but now you have three coefficients, the number of which is determined by the crystal symmetry of the phase, and in particular according to the Laue group of the studied phase. And a convenient way to represent the result is this so-called Warren plot, which goes back all the way to 1950 papers on Warren. As we will see soon, this is a useful and convenient way to represent the results, is a plot of the standard deviation of the displacement distribution as a function of the Fourier length, the distance between couples of atoms in the domain, for different direction in the crystal structure. So this picture gives really a lot of information. Now, what about other sources of line broadening, for example, faulting? Faulting, in this case, I am showing the typical faulting for cubic structure. So is an error in the staking sequence of atomic planes. It is possible to include the effect of faulting in the WPPM approach, that is, as a perturbation of the crystal structure, but only within the limit of low faulting probabilities. That means a diluted faulting. And in this case, we can use a Warren's theory for faulting, which provides real and imaginary parts of the Fourier transform of the faulting line profile component. And this is a function of two parameters to be refined in the Rietveld method, which is the deformation fault probability and the twin fault probability. As I say, this is valid for low probabilities, and in that terms, the main effect that you notice is a broadening, asymmetry, and even a shift in the line profile. Here you see a simple simulation. I will show you later a real case. It is important here to underline, as we will see at the end of my presentation, that in the general case, faulting is a structural problem. So what you need to do is quite different. You cannot just apply a perturbation to the perfect crystal model, which is basically what this WPPM does. So we will have to face the problem in a different way. This will be the very last part of my talk. So, ultimately, it is possible to add various microstructural components which contribute to the diffraction profile, such as, for example, you can add the effect of the relaxation of the grain surface. We have written something on this. You can include antiphase domain boundaries, as in some materials, antiphase domains are an issue. Or you can model inclusions, integrals. You can account for compositional fluctuations. So there is a lot actually you can do with this method, but let me immediately say, give you a caveat, okay, a warning. Everything is valid within the limit of the description we are giving of the line profile, which is based on independent perturbation of the crystal lattice of small but otherwise perfect and average domains. Now, this is quite a tough sentence, so let me leave it there for a while. What I mean that the different effects don't cross-talk. They are handled independently. That's why the convolution approach works in this simple form. It might be possible to combine also correlation terms, but it would become terribly complicated and a little bit pointless. So don't expect this method to work in any possible conditions. So as with many models and theories, it is wrong to think that it can always be applicable. Okay, now it's time to see some applications. So some examples. You can find really plenty of them in the papers. You can Google and find, or you ask me if you are interested. The first case I like to show you uses publicly available data. That was also why I like it. It comes from the ICDD database, the so-called PDF3, which is a subset of the PDF4, which reports experimental patterns together with crystallographic information. So that means I have the data, in this case, for these iron oxide nanocrystals, and even a property sheet which gives some TM picture and then tell us that the mean size has been measured, let's say, around 7 nanometers. The fit is not beautiful, let's say, but this is the data I have. I would suggest always, of course, to collect data which are much better. Maybe you want to use one of these beautiful Rigaku machine or any other machine you like, or you go to a synchrotron. This is really your problem, but my recommendation is to collect good quality data, of course, and extended range, because that allows you to separate the different contributions. In this case, I used the relatively simple model, which is the one that I use most often. The instrument that had been already, say, adjusted and fixed, size term, and a displacement and a strain term, for example, considering some general strain. In this case, actually, there is no strain at all, so the size effect is only present, and the crystals have been modeled as a sort of average spheres, and this is the result. As you see, the distribution of domains is in good accordance with what is stated in the property sheet. So it's about 6-7 nanometers. In this picture, you can also see, in this graphic, you see also how to calculate from the distribution also the so-called volume-weighted mean column length, this L average sub V. Okay, this is the quantity that is generally obtained using the Scherer equation. If you know the appropriate Scherer constant, which for this specific case, a sphere, is 3/4. Actually, the constant is 4 divided by 3, it's the inverse is 3/4. Okay, so clearly here you see that what you get is different, and in general, given a distribution which is skewed, you will have quite a difference between the arithmetic, let's say, average B, as you see in this picture, and the, say, Scherer width. They are different, they must be different. The second case study is a nanocrystalline fluoride powder, which has been produced by high energy grinding in a planetary mill. The demand size is about 11 nanometers. As you see, the fit is quite good. We can even account for a little contamination from magnesium oxide. And you can read the dislocation density that we obtained, around 10 to the 16, quite a high value, cutoff radius. Other parameters like the fraction of age skew, which type of dislocation is present, the unit cell parameter, and also, if you like the detail, the Biwaller coefficients, which, as with the many nanocrystalline materials, is larger, bigger than the bulk value. This is the subject of my recent work. I am not going to talk about that. Again, if you are interested in the effect on nanosites, say, on the Biwaller parameter and coefficient, you can ask. Here, as you see, we see the result for the domain size distribution. And this is in good agreement with what we see in the TM. Actually, with the TM in these systems, you see relatively little. Maybe we are not very good with that. However, you can spot some dislocations. It's known that they form here. So it's correct to use dislocation model, but I always prefer to show, as in this case, the Warren plot. I remind you, this is the standard deviation of the displacement distribution for every distance L inside the crystal, between couples of atoms, along different directions. With this plot, by the way, we see the elastic anisotropy effect with the 111 direction, the HHH direction, which is more deformed than HOO. And this is an intrinsic property of many binary compounds, which have the H00 direction, which is, let's say, the stiff direction, elastically speaking, whereas the HHH is the compliant direction, which is quite opposite to most cubic methods. The Warren plot is preferable because the method I have just shown you, which is based on the Krivoglass-Wilkens theory, has a tendency to overestimate the dislocation density, or even see dislocations where there are no dislocations at all. The reason is because with that method we are attributing the inhomogeneous strain only to dislocations, whereas in the most common cases there are other sources of strain and inhomogeneous strain as well. So in the end, the Warren plot seems to be the best way to represent results, in addition to providing dislocation density, or even instead of providing values of dislocation density. You can repeat the same application. Now, this is interesting case because it's a powder that was not completely ground, and so it's not very uniform. So there are two fractions you see, nearly not ground and heavily ground particles. So you can think of a presence of a bimodal distribution. Here I refine just two fluoride fractions sharing several parameters between the two structures, but then refining two size distribution. And this is just one more application, and is generally possible only if the two fractions are quite different and separated on the dimensional scale. Otherwise, there would be a lot of correlation. Another similar case concerns calcium carbonate. Here you can see some high-resolution TM pictures, evidence of dislocations again. And this is interesting because in this case, calcite is not cubic and therefore shows a much more complex strain anisotropy than fluoride, which is cubic. In this case, in addition to a very good feedback between size distribution, you see around 8 nanometers is clearly the size of these blob-like domains. I remind you, this being heavily milled. There is a good agreement with the TM evidence. It's nice to see the Warren plot again for the different directions, so quite a strong anisotropy as it should be for calcite. And here you can see the quite articulated trend in the contrast factor. You can see also the analytical expression in this case, which represents the anisotropy effect of the strain and then on the broadening of the line profile. Yet another example of calcium carbonate I'm showing you. In this case, with the particular grinding condition, we can see both calcite and aragonite, which is quite common in milling processes. And the pattern can be modeled together with other impurities, quartz, ferrite coming from the mill. And you can get the two size distributions, and using, in this case, this phenomenological model, because it's simply too complicated to model, we obtain the Warren plots for the two cases. By the way, I like to add that in this specific case, we know slip systems for calcite and aragonite. Several, we tested them all, but in the end, none of them seems to work well. And the reason is quite simple, because in this very complex microstructure, inhomogeneous strain comes probably from several dislocations, but also from other effects, grain-to-grain interaction, grain boundary, who knows what else. So this probably is the best way to represent the data, is the most, let's say, honest, instead of seeing dislocation everywhere. Now, let me show you the last example, which actually would be much longer than I will show you, so please refer to this article and the following ones for details. This concerns cubic shaped palladium nanocrystals, which are used for metal catalysts. The distribution of dimensions, as you see, the age of the cube is rather narrow. The distribution you see here at the bottom is the histogram from 1,000 particles from TEM. And also the exact shape of the nanocube is very reproducible. There are no particles, no non-cubic particles. And there is a characteristic truncation, as you see here, of the edges and of the corners. And the pattern can be modeled pretty well in this case. This data collected at 11 BM argon pin mine. And especially for the presence of these interference fringes on the HOO peak. This is an effect that usually people see in thin films or in single crystals, but our powder is a collection of single crystals, all identical, small ones, let's say. But this feature and the quality of the data allow us to obtain a distribution of sizes which is perfectly identical with the TM. This is quite a remarkable result, and is only possible because the shapes are so nicely identical. And in this case, what you see by electron microscopy and what you see by diffraction is identical, which is of course not always the case. Here, grains are crystallites. This is not always the case. In this modeling, we can even refine the exact shape of the cube. We made a model for variable truncation of the cube, truncation of edges and corners, and the little blue shape you see is the best shape we could refine from diffraction, which seems compatible with the TM observations. In this modeling, in addition to including the contribution of the Kapton capillary, because the powder catalyst was in a Kapton capillary, we have also included the effect of the TDS, the thermal, or if you like, temperature diffuse scattering. I'm not going to talk about that, but just that to say that it can be dealt with, and it adds quality to the modeling and further information on the Debye-Waller coefficients. Now, what about the strain in this case? There are clearly no dislocation, but still you have a strain and an inhomogeneous strain. From what? From the surface of the crystals, especially. And then we can use molecular dynamics to make a model of these crystals. So we take these shapes that we have, say, obtained from experiments, TM and XRD. We can make a model using molecular dynamics, which with the embedded atom method potentials works pretty well for simple methods. The picture you see here is the strain field. This is different components of the strain field for these specific shapes, like these three nice cubes in a TM picture. And from the molecular dynamics simulation, we can produce the Warren plot for three direction. Pardon me, the first one is along H00 direction, so it's a cube phase direction, perpendicular. HHO, which is basically this cross section, and HHH, that, as you know, is the main diagonal of the cube. So this is the Warren plot calculated from molecular dynamics, and is shown for two shapes, a perfect cube and a sphere. So first of all, we clearly see that if you repeat the calculation for a sphere, you will get different Warren plots. So it is true that somehow the shape gives an effect on the line profile that can be measured. This is where the XRD results stay. The red dotted line is from the line broadening effect I have described before. And it is nice to see that if we repeat now molecular dynamics just for this shape, so introduce a truncated cube, so not sharp cube, not a sphere, we get the best probably agreement with the experimental results. This has been quite a surprising result for us to see such a good agreement, by the way, between molecular dynamics and experiments, which is not at all trivial. And as I said more on these specific research work, can be seen in the paper and the following ones, especially for the bipolar part. I'm not talking about that because this would be too long. So finally, faulting. As I already mentioned, it is possible to include a term in the convolution for faulting according to Warren's theory, which lends itself very well to the convolutive WPPM approach, but the validity of this approach, as we already said, is only acceptable within the limit of low probability of faulting. This needs to be considered, okay? It's very important. Never try to use it if the fault probability is large. So systems must be diluted, faulting must be diluted. And in this case, as you see now in this example I'm showing here, the main effect on the line profile will be of broadening, asymmetry, and the shift. Now you can read the detail in the reference, but this is a case of plastically deformed, strongly plastically deformed nickel. And in addition to the domain sizes of the order of 9 nanometers, you see the dark field TM picture, we can spot some twin faults, and indeed the probability in this case was in the order of 2-3%, whereas deformation were basically absent. Okay, this is the only way you can deal with faulting within the WPPM approach, which is, in my opinion, quite limited. But now it comes the advantage of a very powerful software like Topaz in the following. As I said before, faulting in the most general case is a structural problem. It cannot be simply reduced to a perturbation of a perfect crystalline domain. So you have to basically model a different structure, a more general structure. Here and below, you would see the effect of increasing hexagonal fault probability in cubic cobalt. Cubic cobalt is assumed to be FCC, but the other polymorph, actually the most stable one, is hexagonal. So it's very likely that in the cubic you might have some faulting. So this is the sequence of faulting for FCC, ABC, ABC, as you know, and for hexagonal AB, AB, AB. So the simulation here was made using Diffraction, which is a software specific to model faulted structure, in general layered structures. And we start with 0%, which is perfect FCC cobalt, and then we introduce a 1%. You barely see it, but the peaks are broadened a little bit. Even there's been some change, other final change. This is 2%, and we keep going on. Around 5%, we start to see some features like this one pointed by the arrow, which clearly do not belong to the cubic structure. And by 20% faulting, you clearly see these features and others which are emerging from the simulation, in addition to increasing broadening and shifting of the profile. And by larger probabilities, you start to see clearly a mix between the cubic and the hexagonal structure peaks. And of course, if you keep increasing at 90%, the pattern is the one of an hexagonal cobalt. And that's it. So this is to say that ultimately, a Warren-like approach can only be used for systems where stacking faults are diluted in a low percentage. And the effects are mainly those of broadening, asymmetry, profile shift, as we have seen, down to 1 or 2% of faulting. This is where you can use that approach. As the percent of fault increases, you need a structural model that actually was used to fit this data and within Topaz. So, low probability gives a main effect on profile broadening, shift, asymmetry, which is very much compatible with the WPPM approach. Larger probabilities give basically something else. And to deal with this problem, For example, you can use in Topaz the so-called supercell approach. And in this case, we see the algorithm here. I'm not going into detail, but multiple layers are basically included in an enlarged unit cell, much enlarged. In this way, we can simulate faulted layers structures with a refinable probability. Now, in this case, this 0.3 is 30% of fixed probability. You might refine it instead of keeping it fixed. Okay, so in addition to working very well and being extremely flexible, the advantage in this Topaz feature is that you can use everything else. The FPA, the fundamental parameter approach model, for the instrumental component, and if you like so, the WPPM macros, for example, for the size and shape of the crystals. Now, to conclude, let me show you a couple of examples. This one, first one, is for the intergrowth of cubic diamond and hexagonal lonsdaleite. The supercell here is made, the pattern is synthesized, let's say simulated using Diffraction. Whereas for the supercell model in Topaz, we use a supercell with 5,000 layers. And then we simulate the different percentages of probability of faults, and we have a nice minimum at around 70%, and even certain spread of values, which depends on the fact that, of course, you can realize the 70% with different stacking models, which then make the minimum a little bit flat. Okay, this was, of course, a simulation, but there are many real studies on faulting, which can be beautifully well treated within Topaz. As I say, this is now a real case study with the disorder of these cadmium planes. I'm not going in this detail, but again, you can refine best fit should in principle give you the probability for the fault. Okay, so in conclusion, while I really thank you for listening this long talk, I point out the two recent articles where you can find these examples, for which I have also published some data in the input files for Topaz, and where you can find reference to previous work on this approach. And for any other needs, you just email me or take a look at ResearchGate or my Google Scholar and our still actually work in progress website. Thank you very much for your attention.